Yeah, no, thanks. Thanks for inviting me. So my talk, I think it's, you see my screen, right? Yeah, I think.
Yeah.
So I believe it's called dimers, networks, and integrable systems. So in this talk, I will describe two constructions of integrable systems and discuss a connection between those two. So let me say right away that for the purpose of this talk, by an integrable system, I basically mean, so we have a Poisson manifold M, and on this Poisson manifold, we have a collection of functions fi. So these are functions on M, and they're pairwise Poisson commute. So that's all that we require. A standard definition of an integrable system is to assume that there are sufficiently many of them so that the level sets of those functions are Lagrangian submanifolds. But we really will, and in sufficiently nice examples of constructions we will discuss, this is indeed so, but we really won't care much about this condition. So for this talk, just a collection of Poisson commuting functions on a Poisson manifold. And well, people study these integrable systems a lot. In particular, well, people who study dynamics care about this a lot. And one of the central problems in this field is construction of such systems. So how the question is, well, how to construct sufficiently many Poisson commuting functions on a given Poisson manifold. And today I will talk about two such very general constructions, and both of these are coming from combinatorics, and well, they are both have been known for quite some time. And the main result that I'm hoping to explain is that essentially those two constructions are almost equivalent to each other, with some exceptions. So the two, first I will explain what those two constructions are, and then I will talk about the relation between them. So the first construction we'll discuss is the so-called Goncharov-Kenyon systems. So this integrable systems, their construction is coming from what's called the Dimer model. So the Dimer model is a model in statistical physics, and well, the basic object that's considered by this Dimer model is a bipartite graph. So a bipartite graph is just a graph whose vertices are colored black and white, and you can only connect by edges vertices of different color, like this. And then a dimer or a dimer cover, or which is the same, a perfect matching on a bipartite graph, is a collection of edges with a property that every vertex is incident to exactly one edge. So, and that well, sort of explains the name for this, so the Dimer model. So in physics, people think of these graphs as collections of particles, say atoms, and then edges in the graph they represent, and there are two kinds of atoms in this model, black and white. And edges, they represent possible bonds, and then the choice of a perfect matching describes a way how these atoms can join together to form dimers. Dimer is just a polymer with two atoms in it. In this case, it should consist of one white and one black atom. So this is a quite classical model in statistical physics. And what Goncharov and Kenyon did, they explained how to use this model to construct an integrable system on a certain Poisson manifold. So let me explain the construction of this system. So first of all, well, this is also something coming from, so in statistical physics, people talk about probabilities. So for a given bipartite graph, it's possible to have several perfect matchings or several dimer covers, and then people want, well, basically to compute the probability of every given dimer cover. And for that, one needs to introduce probabilities of each particular bond. And we're going to use this for our integrable system construction. So we won't really be thinking of them as probabilities, but that's where this thing is coming from. So first of all, so we will consider a bipartite graph, and moreover, it will be a weighted bipartite graph. So weighted just means that to every edge we assign a weight. We can think of this weight as a formal variable or as a real number, and then having a weight for every. Sorry?
Is it a directed graph?
No, it's not directed, even though, I mean, since it's a bipartite graph, it has a canonical orientation. For instance, you can orient it from black to white or white to black. We will be considering certain directed graphs later. So we will be discussing the second model, and in the second model, we'll have directed graphs. But here, no.
Okay, thanks.
So just a graph with the weights assigned to edges, and then having weights like that, one can define the weight of perfect matching as just the product of weights of edges that constitute the matching. So for instance, here, the weight of this blue perfect matching is x1, x3. And then, well, to turn, and well, in general, we cannot construct an integrable system from a bipartite graph. To get an integrable system, Goncharov and Kenyon, they consider a weighted bipartite graph that's embedded in a torus, two-dimensional torus. So now we have a weighted bipartite graph on a torus. And then, well, if we have a graph like that, then, so what we're gonna do, again, we're gonna look at all perfect matchings, compute the weights of those matchings. But here there is one additional piece of information that one can assign to a matching. Namely, well, as I said, even though the graph is not oriented, one can orient it in a canonical way. And therefore, if you have a matching is a collection of edges, but because these edges can be oriented, this can be viewed as a one chain on the graph. And by definition of a perfect matching, if you consider it as a one chain, you compute the boundary of that one chain. That's going to be the sum of all black vertices minus the sum of all white vertices, because, well, every black and every white vertex is incident to one single edge. And what that means is that all perfect matchings considered as chains, they all have the same boundary. So if you consider the difference of two matchings, that's a cycle in this graph. And this allows us to compute the homology class of that cycle. And therefore, we can also talk about homology classes of perfect matchings. They're not exactly well defined because matchings themselves are not cycles, but they're defined up to shift. You can fix a reference matching, and then for any other matching, you can subtract that one, compute the homology class. So for every matching, you can define its homology class. And after that, so Goncharov and Kenyon do the following thing. So they say they fix some homology class, gamma of this torus, so it's a homology class with integer coefficients. And then we can consider all perfect matchings that belong to that class. So we consider sum over all matchings belonging to the class gamma, and for each of these matchings we compute its weight. So it's just the product of weights of edges in the matching, and we add up over all matchings in the given class, and well, that gives us a function h gamma. So for now, well, this function, well, it depends on the weights of edges. So we can think about the space of all possible edge weights, which is just the same as the space of real or complex, whatever the base field is, functions on the edges of the graph. And we obtain this functions h gamma. And then the main result of Goncharov and Kenyon is that in a certain sense, this functions h gamma, they form an integrable system. Of course, for that to make sense, we need to say what the Poisson structure is. And this Poisson structure, it's not defined on the space of edge weights itself, but one needs to take a certain quotient of that space. So namely, observe the following thing. So let's consider, say, some white vertex of our bipartite graph. And then by definition of a perfect matching, there is exactly one edge in every matching that's incident to the vertex. So therefore, so now let's do the following operation. Let's consider all edges that are incident to the given vertex and multiply their weights by the same number lambda. So if we do that, then clearly the weight of any perfect matching will be multiplied by lambda, because there is exactly one single edge. Out of those whose weights we multiplied by lambda, there is one single edge in every given matching. Therefore, well, what happens under this operation, and this operation is known as gauge transformation. So what happens under such a gauge transformation, all functions h gamma are going to be multiplied by the same factor. So therefore, and by the way, it doesn't have to be a white vertex, could be a black vertex as well, doesn't matter. We can do this transformations at any vertex, we can compose them together, and these functions h gamma under such transformations, they all just change by a common factor. Therefore, if we, so now instead of thinking about this functions just as they are, we will think of them as defined up to a common factor, and regarded like that, they're defined on the space of edge weights mod gauge transformations. And it's not hard to see what that space is. So the space of edge weights, assuming that the weights are non-zero, we can think of that space as the space of one co-chains or co-cycles, which is the same of our graph with coefficients in the multiplicative group of the field. So let's say C star. And then what these gauge transformations are, well, this simply change our co-cycle by a co-boundary. So this space here is simply the cohomology group. So if we call our bipartite graph gamma, this is simply the cohomology of gamma in the multiplicative group of the field, so say C star. So, and then we consider this h gammas as functions on this cohomology, and they define up to a common factor. And the last ingredient that's needed here is the Poisson structure on this space h1 gamma of C star.
Excuse me, I missed. So how come the function on cohomology? So you explained that to each dimer corresponds a function, right? And also a cohomology class. But in principle, why it cannot be that the functions are not different?
So let me see if I understand your question. So first of all,
or you are summing up over all elements representing given class.
So this, well, each of this, basically, so I'm thinking of weights as functions on, so let me see. All right, so let's say so the space of edge weights is well, each is a space of assignments of weights to edges. So we can think of this assignments as co-cycles. And therefore, initially, this functions h gamma. For each fixed gamma, h gamma is a function on the space of one co-cycles. But then, as I explained, when we change a co-cycle by a co-boundary, all these h gammas, they change by a common factor. Therefore, we do, well, h gammas are not well defined, but if we, so we can consider h gamma 1, h gamma 2, and so on for all classes, and we want to, so up to a common factor, so we can view this as a map to a projective space of a certain dimension. This is a well-defined map on the cohomology of the graph.
And can you repeat, so why common factor?
So, well, basically changing by a co-boundary, since we are in a multiplicative group. So co-boundary, let's say we take a zero co-cycle that is just concentrated at a single vertex, right? So this forms a basis of co-cycles. So then the co-boundary of that co-cycle is, well, it's simply lambda sitting on every edge that's incident to that vertex, right? Because all edges are oriented in the same way. And in our perfect matching, there is exactly one edge that belongs to that collection. Therefore, the weight of the whole matching will be multiplied by that factor lambda.
I see. Okay. Thank you.
Does that make sense?
Yes, thanks.
Okay. So now I will say just a couple of words about the Poisson structure, because the Poisson structure is not very much relevant to our discussion. So I'll just briefly explain what that is. So, well, first of all, if we have any surface, then there is a natural Poisson structure on the cohomology of that surface. Namely, well, let's consider two functions that are two linear functions on the cohomology, and linear functions on the cohomology, they're just homology classes. So we have two homology classes, A and B, and we define their Poisson brackets. Since they're homology classes, we can compute their intersection number. And we define the Poisson bracket to be the intersection number times their product. So this is a Poisson structure. So if this is surface S, this gives a Poisson structure on the cohomology of S with coefficients in the multiplicative group of the field. So this is defined for any surface. And so what we do in our case, well, we want to define a Poisson structure on the cohomology of the graph. And for the graph, of course, this doesn't quite make sense. But instead of considering the graph itself, we consider a neighborhood of that graph in the surface, and that gives us a surface with a boundary or a fat graph, if you like. And then for that object, we can consider this Poisson structure. But this Poisson structure itself, it's not very interesting because, well, from the definition, it's clear that all cycles that are homologous to boundary components, they are in the kernel of the Poisson structure because they have zero intersection with everything. So the Poisson structure, and if we have a graph on a torus, we consider a neighborhood of that graph that has a lot of boundary components. So they just correspond to all faces of the graph. So this gives a very degenerate Poisson structure. The rank of the intersection form is it's equal to 2. It's very low. So it's a very degenerate Poisson structure. It's not very interesting. And the Goncharov-Kenyon Poisson structure is obtained like this. So you take this blue surface with boundary, and you take every edge and you cut the surface like this, and then you glue back, but with opposite orientation. You do that for every edge, and this again gives a surface which is orientable, not hard to check. But now this surface, it has much less boundary components, and well, the intersection form still has a kernel, but this kernel is much smaller. And well, the main result of Goncharov and Kenyon so this produces it gives a Poisson structure on the cohomology of this surface with boundary, but it clearly retracts to the graph. So it also gives a Poisson structure on the cohomology of the graph.
I'm sorry, what is your logic between using a bipartite graph? Why are you having like black and white ones? Why not just take a regular random graph?
Well, you could take a regular graph, definitely, but it's not clear how to construct an integrable system in that case. So here, the construction is essentially based on the graph being bipartite. So, I mean, in principle, yes, one could, of course, define the notion of a perfect matching for an arbitrary graph. I don't think that this gives an integrable system.
But where exactly in the formulas that you've described would it fail the construction if you just use a random graph without the bipartite part?
Well, first of all, this you won't be able to consider this quotient here, I believe, because that okay, is what I'm saying correct? No, I think it's not. So I think for what I've said so far, it probably not uses essentially that the graph is bipartite, but and the main result of Goncharov and Kenyon is that these functions H gamma on the cohomology of the graph, they Poisson commute with respect to the Poisson structure that I just described. So I think this result doesn't hold for general graphs. So the proof of that essentially uses the bipartite structure. It might be the case that things I've said, at least in some form, apply to general graphs. Yes.
Okay, thanks.
Okay, so, and well, of course, there are infinitely many homology classes for the torus, but it's clear that we cannot get infinitely many Poisson commuting functions, well, at least not independent ones. But in fact, here it's clear that all but finitely many of these functions are zero, because each of the function is a sum over certain perfect matchings, and a finite, we consider a finite graph, and it's clear that a finite graph may only have finitely many perfect matchings. So in fact, this gives a finite collection of functions, and the result of Goncharov and Kenyon is that they Poisson commute, moreover, if the graph satisfies certain additional assumptions, then this is well, what's classically known as an integrable system. So this is a complete collection of Poisson commuting functions. So that their number is maximal possible, the fibers are Lagrangian submanifolds, and so on.
Could you please repeat how you choose these green segments?
So the green segments are just, well, you consider the fat graph, so the neighborhood of your graph in the torus, and then the green segments are just transversal to every edge. So say you can take the midpoint of the edge and consider curves that are transversal to the edge, go through midpoints.
And so for every edge, you cut and reglue the same edge.
Yes, exactly.
Okay, thank you.
Because yeah, you do, if you do it for every edge, you again get an orientable surface.
No, it probably would be useful if you give an example, maybe simple example where we can see this Poisson structure in some situation.
Sure. Yes. Okay. So let's try. So first, this Poisson structure, it's a Poisson structure on cohomology. Functions on cohomology can be thought, well, as basis of functions, we can take cycles. Cycles in the graph, they are functions on cohomology. So what we want to do is compute the Poisson bracket of two cycles. So let's say we have a cycle, something like this, and we had a cycle which goes like this. So then, well, if we just took the fat graph and we would use that fat graph or the neighborhood of the graph to compute this bracket, we would get 0 because these cycles, they do not intersect there. But by doing this operation, so here is, well, we can take the neighborhood of this edge here. And then before we reglue one cycle, it goes like this. And another cycle goes like that. So by doing this regluing thing, what we basically do, we create an intersection between these two cycles. And therefore, so if two cycles, they share one single edge like that, then the intersection number, it becomes, well, with a certain orientation, so the intersection number is 1. So here, the Poisson bracket between this cycle and this cycle will be the product. And in general, well, it is related to basically how many edges the cycles have in common.
Fantastic, thank you.
Sure.
Can I ask, sorry, one more question?
Yes.
So where in the story do you use that the bipartite graph is contained within the torus, is embedded on the torus?
So again, for the construction, I'm not really using that. So one could repeat the same construction for an arbitrary surface, and the Poisson structure is still defined. It's just not true in general that this gives an integrable system.
Thanks.
So, but in, yeah, no, in the construction, I was not using that. So one could definitely do it for higher genus surfaces. And I think this case is still not well understood. So yeah, they do not form an integrable system. I think they should still have some nice properties, but it's essentially, I think it's widely open.
Okay, thank you. Or I guess the reason I ask, because like it looks like when you do this process where you create this graph, sorry, where you create this this fat graph, like that now gives you a bipartite graph on some different surface. So well, it looks like there's some.
Yes, but it is for the Goncharov-Kenyon result, it is essential that you start with the torus. Yeah, okay, but certainly after regluing, you get the genus of that surface is much higher than that. Yes.
Okay. Right.
It is related to how many faces you had in the graph. Are there any other questions on this part? Okay, so we've described one construction, and so this is from Goncharov-Kenyon paper. So it is from around 10 years ago, and now I will describe a different construction of integrable systems that's also related to certain graphs, and these graphs are known as perfect networks. So the notion of a perfect network, it was introduced by Postnikov in 90s, and initially it had nothing to do with integrable systems or Poisson geometry. So it was basically a combinatorial object, and Postnikov used these networks to study total positivity, in particular totally positive Grassmannians. And the Poisson geometry related to these perfect networks, it was described in a series of papers by Gekhtman-Shapiro and Vainshtein, and then also by Gekhtman-Shapiro-Tabachnikov-Vainshtein. And I will, in particular, this paper, it contains a construction of an integrable system based on the notion of a perfect network, which I will now describe. So first of all, what's a perfect network? Perfect network, it's again a graph. Now it's a directed graph, and moreover, it has some additional properties. Again, it has two types of vertices. One is called white, the other is called black, even though it's not necessarily bipartite. So we are allowed to connect vertices of the same color now. But the additional requirement, so perfect here, means the following thing. So each white vertex has exactly one incoming edge. So it may have any number of outgoing edges, including 0 in principle, but it should have exactly one incoming edge. And then every black vertex has exactly one outgoing edge. And we only have vertices of these two types. And then we are allowed to connect them in an arbitrary fashion, but these two conditions, they should be satisfied. And a graph like that is called a perfect network. And so now, again, to get an integrable system from this, we consider a perfect network that lives on a torus. And here, the construction is, it goes like this. So first of all, we want to cut this torus to get a cylinder. And so after cutting this, so we're going to cut a torus along a simple loop to get a cylinder. And we want to choose the loop in such a way that, so after we cut it, well, clearly the cut will intersect some edges, and this will form some vertices that live on the boundary of the cylinder. And we want to make the cut in such a way that the vertices living on one boundary are all sources, and the vertices living on the other boundary, they're all sinks. And for an arbitrary perfect network on a torus, that's equivalent to saying that when we make this cut, then the cut intersects all edges with the same orientation. So that may be impossible initially, but there is a way to somehow fix the graph so that this is possible. So namely, there is an operation on those graphs that's called cycle reversal. So you take a directed cycle in the graph and you reverse orientation of all edges. And it is known that by doing some cycle reversals, one can arrange so that this condition is satisfied. And then we can cut along a loop to get a network on a cylinder, which has this property that so all edges on one boundary are sources, all edges on the other boundary are sinks, and the edges that are inside, they still have not edges but vertices. The vertices that are inside, they still have this property that well, they satisfy the perfect condition. So every one of them either has one incoming edge or one outgoing edge. And then, so here, instead of counting perfect matchings, we count paths that go from sources to sinks. And it's again a weighted count. So there is a weight assigned to every edge. And then the weight of a directed path is defined again simply as a product of edges on that path. And then for every I, so we choose some source, we call it I, we choose sink, and we call it J. And then we look at all paths that go from source I to source J, and we compute the weights of all these paths. And we add them up, and let's call the resulting quantity Mij. So it's sum of weights of paths going from I to J. And this should actually be taken with certain signs. And the sign is related to the topology. It's not just signs. So first of all, there are paths that are simple, non-self-intersecting. They just go from a source to a sink without self-intersection. And for such paths, the sign is positive. But then there may be paths that intersect. A path may intersect itself, and in that case, the sign is it's the parity of the intersection number. So if the path is intersecting itself once, then the sign is negative. If the path intersects itself even number of times, then the sign is positive. So I'm going to put plus minus here. So the sign is determined basically by the topology of the path. And then there is one additional thing that needs to be taken into account. Because we have a cylinder, we can also, well, distinguish paths by their homology classes, by counting how many times the path winds around the torus. And we basically count this. So to every path, we can assign an integer, which is basically the homology class, and then we form a generating function. So we multiply this by lambda to the power of j, and j counts how many times the path goes around. So one way to define this rigorously is to make a cut on the cylinder like this. So cut it from one boundary to another. And then when a path intersects this cut, so you compute the signed intersection number of your path with the cut. So when you intersect once in the positive direction, you multiply by lambda. If you intersect in the negative direction, you divide by lambda. So therefore, we get a function Mij of lambda. Well, it's quite natural to form a matrix out of those functions. And well, this and then the main result of Gekhtman-Shapiro-Tabachnikov-Vainshtein is that it's possible to produce an integrable system out of this matrix. And again, here the entries of this matrix, they depend on edge weights. So these are functions of edge weights. But it's possible to define the notion of gauge transformation, which is very similar to what we had for bipartite graphs, and one can mod out by this gauge transformation. So it's a similar setting. So we get, eventually we end up with functions on the cohomology. And then the integrable system here is defined by taking, so this M, it depends on lambda, so it's a matrix that depends on a parameter. And then one can take the characteristic polynomial of that matrix, which is a polynomial, which is a function of two variables now. It's lambda and mu. And then one can take the coefficients, expand this in terms of lambda and mu, and take those coefficients, and then what's proved by Gekhtman-Shapiro-Tabachnikov and Vainshtein is that those coefficients, they form an integrable system, again on the same space, basically on the cohomology of that initial graph on a torus. So here we work with a cylinder, but this cylinder, it's initially obtained by cutting a torus, and one can show that, well, this gives a well-defined functions on the cohomology of the torus. So that's, I want to explain the details of this construction, but that's basically how it goes. And then the main result of my recent paper gives a precise relation between these two constructions. So it turns out that in some sense, these two integrable systems, they are the same. So let me explain what I mean by that. So, well, first of all, of course, well, to say what it means that they're the same, we should explain what the correspondence between the initial data for these systems is, because one construction is based on a, well, it starts with a bipartite graph on a torus, and the other construction starts with a perfect network on a torus. And first, one should define a map between these two sets, because, well, otherwise it makes no sense to say that the corresponding integrable systems are the same. And this map is pretty simple. So we start with a perfect network on a torus. So it's a graph with vertices of two types, white and black. And it may turn out that this graph is already bipartite. So in that case, we don't need to do anything. The only thing we need to do is forget the orientations of all edges. This produces a bipartite graph. So we can go from here to here. It may happen, though, that there are edges for which both vertices are of the same color. Then we do a very simple thing. We just insert a vertex of an opposite color in the middle. So in that way, we can go from a perfect network to a bipartite graph. That's clearly not a bijection, though. But there are some natural operations on these two types of graphs that do not change the corresponding integrable system. So for instance, if you have in a bipartite graph, you have a white vertex of valency 2, then what you can do is remove that vertex and contract this edge. And it is very easy to show that this doesn't change weights of perfect matchings. So the integrable systems associated with the two graphs are the same. So there is some natural equivalence relation on bipartite graphs, which preserves the integrable system. And same can be defined for perfect networks. And then if we mod out by this equivalence relation, then it turns out that what I've just described, it's a bijection between these two types of graphs. And then the main result is that this bijection actually identifies the corresponding integrable systems, but not exactly and not always. And to state the precise result, first of all, I'm gonna return to the Goncharov-Kenyon construction. So here we define this Hamiltonians for each homology class. We get a Hamiltonian. So to state the main result, I want to consider the generating function of those Hamiltonians. So this generating function is basically, so for each homology class on a torus, we have a function. So now I want to consider the sum. So I choose a basis in the homology of the torus. So I consider, if I choose a basis, then a homology class is just a pair of integers, ij. So I sum over all homology classes of the torus, and I form a generating function. So I have a Hamiltonian that corresponds to the class. I multiply by lambda I mu to the power of j. And also there are certain signs here, which I won't explain in detail why we need to, but why we need those signs. But basically what we consider is a sort of a signed generating function of those Hamiltonians. It just turns out to be more convenient to work with a signed generating function than just usual generating function.
Well, I think the signs come from the fact that you're using directional graphs. You're using a bipartite graph with black and white vertices.
So
if you didn't have that, the signs would be irrelevant.
I'm not using directions for, so for now, I'm talking about the Goncharov-Kenyon construction in which we have an undirected graph. So there are no directions there.
That's the directions that you mentioned, the vertices in the perfect network where you have one line going in and the others going out. That's what a directional graph is. When you're already defining a construction of your lines, which way they have to go, that's where the signs come from, the pluses and the minuses.
Okay, let me say this. So we do indeed have signs here, but the signs, they're actually sort of simple in the following sense. So we have a certain sign, so we need to assign a sign to every homology class, because summons here, they correspond to homology classes, right? So we need to, for every homology class, we need to choose either a plus or a minus. So so for every pair ij, we need to choose a sign. And the rule is quite simple. So first of all, the sign only depends on the parity of I and j. So it doesn't really depend on the homology with integer coefficients. It only depends on the homology class with coefficients in Z2. And there are only 4 homology classes with coefficients in Z2. There are only 4 possible parities. And then the rule is that for 3 of these 4 classes, the sign should be positive. For 1, it should be negative. And well, again, there are 4 ways to assign signs like that. And the particular choice is not important, because it's clear that here, if we replace lambda by negative lambda or mu by negative mu, then we're gonna go from this choice of signs to a different one. So this is the rule. And it doesn't seem to be related with the orientation of the graph. This is something that's related to the notion of a discrete spin structure on a surface. And it basically comes from, so there is this classical way of counting perfect matchings for graphs on surfaces that's known as Castellan's theory, and the signs that are coming from Castellan's theory. And I wouldn't say that this is because the graph is oriented. At least I don't see how we could possibly avoid this science by considering general graphs. Well, maybe
I would only say, I think you're definitely more on the mathematical geometry side. If you're interested to look more into these signs and random graphs, you should definitely just try looking into graph theory without any geometrical applications. I don't know the paper that you're using. That's probably what it is. That's probably the construction that they just set out by default. I don't know why. But if you are interested in learning more about this, I would definitely suggest it. And that's where the neural networks come in, because the graph theory is the basis, which is used for neural networks and networking. So like deep learning algorithms that artificial intelligence everybody is using right now, what you're describing, that's literally the building blocks where it comes from. So if that's something that you're interested in learning more about and digging deeper into it, maybe you should read about it.
Okay, thanks. All right, so where was I? So, okay, so I want to describe the precise relation between two integrable systems that we've described. So as we saw, one of those can be so the Hamiltonians. We take the Hamiltonians and we form this sign generating function from them. And this sign generating function, it basically contains exactly the same information. It's just a way to encode the Hamiltonians. And the other integrable system, it's encoded by this characteristic polynomial of the matrix M of lambda. That's what we associate with a network. So now we want to relate this object with a generating function K of lambda mu. And in order to do that, well, first of all, it's convenient to rewrite the characteristic polynomial in a different form. So namely, we consider, instead of considering M minus mu times the identity, we will consider we will write the characteristic polynomial in a different form, but that's basically the same, just a change of variables. It just seems to be a more convenient form here. So, and we want to relate this to the function K of lambda mu. And one thing that needs to be said here is that, well, K of lambda mu, it's a polynomial in lambda and mu by definition. So this function here is actually not a polynomial, because recall that we defined that as a sum over all paths in a directed graph. But if we have a directed graph that has cycles, then there are actually infinitely many paths. So this M of lambda, it's not really a polynomial, but it's in general, it's a power series in lambda. But it's well known that if you have a directed graph and you start, well, counting this path and their weights, and you add these things up, then this formal power series that are obtained, they're actually always rational functions. Because basically, as you go around cycles, you start counting the same cycle more and more times, and you just get a sum of a geometric sequence. Therefore, all this formal series, they can actually be rewritten as rational functions. And it follows from this that this determinant, it's polynomial in mu, but in lambda, it's a rational function. So in contrast to this K of lambda mu function here, we get something that's rational in lambda. And then the main result that I proved, so let me state it, and then I will probably say just a couple of words about the proof. So the main result is that there is a simple relation between these two objects, namely that the determinant, this characteristic polynomial, can be computed using this generating function K of lambda mu in the following way. So well, this is a rational function. The numerator of this rational function is just K of lambda mu, and the denominator is K of lambda 0. So that's the relation between them. It looks a little bit strange because there is some strange break of symmetry here. Like initially, lambda and mu, they played exactly the same role, and they're related to a choice of basis and the homology. But this is because, well, in the second construction, we choose a cycle along which we make a cut. And this mu variable is related to the choice of this cut. Therefore, the symmetry is broken. And basically what this says is that the two integrable systems are more or less the same because, well, the generating functions of the Hamiltonians, they kind of coincide. There is an exceptional case though. So what may happen here is that, so here we divide one polynomial by another. It may happen that these two polynomials, they have a common factor. They have a common factor that will cancel out, and therefore there will be more Hamiltonians in the bipartite construction as compared to the perfect network construction. But this situation, it's not really common because, well, it means that these two polynomials here, they're not co-prime. And if that happens, that can always be fixed because, well, as I said, this new variable here, it's related to a choice of a cycle along which the cut is made. So, and it's not hard to see that, well, simply because a polynomial can only have finitely many factors, then there are only finitely many cycles for cutting along which we can get the situation that there is a cancellation. So as a result, well, it may happen that these two integrable systems are not the same, but this just means that we cut along a wrong cycle. One can always find a cycle cut along which one gets exactly the same. The two integrable systems, they become exactly the same. And I think I'm basically out of time, so let me just say what the main idea of the proof is. So, you know, both constructions here, they're combinatorial, but I don't know how to prove this in a combinatorial way. So this seems hard because, well, these two objects are quite different nature. And in both constructions, they involve certain signs, and it's not clear how to relate those signs. So the main idea of the proof is to consider, well, basically to bring some geometry. And so what I do, instead of just considering a graph on a torus, I say, so let's assume that our torus is given a flat structure. So we are considering a torus with a flat metric on it. And the graph, it's not just an abstract graph on a torus, but it's a graph that's embedded in a flat torus with a flat metric. And the edges of the graph are straight line intervals. And this cannot be done for a general graph on a torus. There are obvious abstractions. For instance, if you have a loop, then there is no way you can make that a straight line interval. But again, we have a certain equivalence relation on the graph. In particular, well, if we have an edge, we are allowed to add more vertices along that edge. So we can take sort of a subdivision of the graph. And it's clear that if you take a subdivision that's fine enough, then you can arrange so that the graph can be embedded in a flat torus with straight line edges. And then after that, so what you get is basically sort of a polygonal subdivision of a, so torus is subdivided into polygons. And I use the geometry of that subdivision to relate the two constructions. In particular, well, the angles of those polygons, they play an important role here. And I found a way to express both of these objects, rewrite them in terms of those angles of polygons. And after doing that, one is able to show that these things actually coincide. And I'll probably stop here. Thanks for listening.
So thank you very much, Anton, for your nice talk. Any questions from the audience?
So
yes,
you have this equivalent. Well, you have an equivalent. You have a relation between the equivalence of dimer models mod sum relations and these directed graphs mod sum relations. So the is the set of equivalence relations on the dimer models like dimer mutation, or is it smaller than this or broader than this?
So I guess by dimer mutation, do you mean this moves that are considered by Goncharov and Kenyon, or so?
Yeah, sure. Yes, I guess
So
this is if you take like the dual quiver mutation of that.
Okay, okay. So it is smaller. It is smaller. So in particular, well, in Goncharov-Kenyon construction, there is a move that corresponds to a quiver mutation at the 4 valent vertices. So this is basically, so if you have something like this, then you add an additional square here. So this is called an urban renewal move, or which if you think about the dual quiver, that's a quiver mutation at a 4 valent vertex. So I don't allow this. So it's a smaller class. So basically for bipartite graphs, what you're allowed to do is you can, if you have a 2-valent vertex, you can remove it and contract the corresponding edge. So that's pretty much all that you can do for a bipartite graph. So for a perfect network, you can do more things. So for a perfect network, you can simply erase 2-valent vertices. You can contract edges if you have same color vertices joined by an edge. And one operation, other operation is reversal of direct cycles that you can do as well. Because, well, when we go from networks to graphs, we forget the orientation. By allowing reversal of by modding out by these reversals, can basically, well, you cannot recover the orientation exactly from a bipartite graph, but you can recover it up to cycle reversals.
And then maybe a follow-up question to that. So you mentioned that on the dimer side, you have this quiver mutation, which you could do at 4-valent vertices, but we don't know in general how to do quiver mutation at higher vertices. If I looked at the directed graph side, is there kind of more flexibility there that would allow me to see that, or the story is almost exactly the same?
I'd say it's the same. Yes. So for this perfect networks, it's called Postnikov moves, and this Postnikov moves there. Well, they're just exactly the same mutations, just in a different language. So again, well, yeah, it's a very good question. So how to, because the problem with mutations at higher valence vertices is that they're not planar. So they're not local. And because of that, we had a graph on the torus with doing mutation like that. And then there is no natural way to embed the result in. It doesn't embed in a torus, and there is no natural way to embed it somewhere. So yeah, it's not very clear how to interpret those.
Yeah, thank you.
May I ask you, so in these integrable systems, what are the invariant Lagrangian submanifolds? Do you get tori, so how they're embedded and so on?
So I don't know of a good way to describe them. Well, first of all, this, as I said, in general, it's just a collection of Poisson commuting functions. So there are some additional conditions on the graph that are needed for the collection to be complete so that you get this Lagrangian submanifolds. But I mean, I don't know of any, I mean, okay, for a general integrable system, how do you describe what are the Lagrangian submanifolds?
No, I can tell you. So which questions are interesting for symplectic topologies, right?
Mm-hmm.
So okay. So first of all, in your situation, it's even unclear that these joint level sets of the integrals are compact, right? So I mean, at least, I mean,
yes. Well,
assume they are.
Some of them are, yes.
Yes, so then you have tori, which live in certain symplectic manifolds. And there is kind of meta principle that invariant tori of integrable systems sometimes produce interesting Lagrangian submanifolds. So for instance, Lagrangian knots or some kind of things with special rigidity properties. And for symplectic topologies, let's put it in this way. So this type of construction could in principle serve as source of interesting examples, which are otherwise, I mean, not clear where to find. Yes. But for this, of course, some certain exploration should be made, and in particular, it would be nice to see a general picture. So, for instance, you basically even didn't tell us what are symplectic leaves of your kind of Poisson structure. Yeah, so whether you have some interesting symplectic leaves and let's say Lagrangian tori in these leaves.
Now, symplectic leaves here are not hard to describe because the Poisson structure basically, well, by the way it's defined, it's the Poisson bracket of two variables is equal to their product. So in terms of logs of these variables, it's a canonical Poisson structure. So the symplectic leaves are quite easy to describe. So we can say what the Casimirs are. So this is not hard, but describing the Lagrangian fibers, well, it is of course hard because this weights, well, the Hamiltonians, they're polynomials of some high degree. And I think usually questions like that, people are only able to answer them in quite simple examples, right? In low dimension, some simple integrable systems. This is, in general, I would expect it to be very complicated for systems like that, but I may be wrong, of course. And I don't think much is known in that respect.
Yeah, but I would say that dimension 4 could be interesting, and dimension 6 is certainly interesting. So
no, I agree. I'm just trying to say that this is, I mean, if you look at all known examples of integrable systems, this is definitely not the simplest one. It's kind of, it might be just hard to work with it. So, I mean, yeah, it's just one of the most, it's on the complicated side, I'd say. So it might be hard to answer questions like that. Certain things can be said though, but I mean, I would expect this to be a hard question. And I cannot say more.
Thank you.
Yeah, no, sure. Thanks for the question.
Any more questions?
One more question, just to refresh my memory. You said that the integrable system was defined on H1 of the ribbon graph associated to the dimer.
You can think of it as just the graph itself. I mean, it's the same, right? So the ribbon graph is just the neighborhood of that graph, so it contracts to it. So you can think of H1 of the bipartite graph with coefficients in the multiplicative group. Yes, that's where it's defined. For both constructions, essentially. Yeah. Well, I mean, we do show at the end of the day that they're the same. So.
Okay. Thanks.
More questions? Okay, if not, we thank the speaker again. Thank you, Anton, for the talk.
Thank you.
So if people want to keep on discussing, people are welcome to stay. So I'm just gonna leave you guys now. So thank you very much again, and thank everyone for coming.
Thanks, Augustine.
Yeah, thank you for for having us, and sorry for the mix at the beginning.
No, that's okay. No problem.
Yeah. I guess it happens, but it's also pretty early for you, right?
Yeah, it's what, 7 now, was 6:15. We started.
It was a heroic act. So
It was a heroic talk.
yeah, thank you very much, Anton. It was beautiful talk.
Thanks, Lenny.
Okay.
Bye.
Bye, everyone.
Anton, if you have a quick moment, maybe I can run some ideas and questions past you. So
sure, yeah.
There's a way to associate to a dimer on a torus a Lagrangian inside of C star squared, whose topology is this ribbon graph. In which case, H1 of the Lagrangian describes the deformations of it, and this is supposed to be some kind of symplectic space. So I think maybe like one interpretation to these Hamiltonians that you're describing, this integrable system, is some kind of integrable system on the moduli space of a certain Lagrangian submanifold. There's also some kind of story which is supposed to tell you that there's a way to mutate these Lagrangians, but it's not really known how they kind of relate to dimer mutations, because dimer mutations kind of aren't well understood. I haven't, I'm like really haven't learned anything about the integrable system story before I saw your talk at the word dimers and so I decided to attend to it. But
Do you have any references for what you're saying?
Yeah,
I think I've seen these things, but I don't know the detail.
Yeah, it's a paper that I worked on, which is why I have so much interest in it, and bringing it up now. I can send it to you in an email if you would like.
Sure. Yeah, of course.
So how did you come to look at, like, was it kind of known that there was supposed to be a connection to these directed networks, or was this like, I'm like, how did, like, those don't seem like two objects which would be like kind of naturally related to?
Well, there are, yes, there are. I mean, well, first of all, the both constructions were motivated by certain examples, and there were quite a few examples that were known sort of to fit in both and that were described from both viewpoints. So it's, well, it seems natural to try to connect the two constructions in full generality. Yeah, and I mean, I think people in combinatorics, they kind of use both objects interchangeably quite often. So they're definitely not completely unrelated.
Yeah. And you said earlier that, like, the story kind of completely breaks if you start trying to work on surfaces which are not tori for your timer.
Again, I don't think it completely breaks. It's just, well, it doesn't go through in exactly the same way. It may still be, well, again, so when Goncharov and Kenyon wrote their paper, they basically announced that they will generalize this to higher genus surfaces. This never happened.
Oh, okay.
So it's known that it doesn't work directly, but it may still work somehow. But I'm not sure what exactly one needs to do in that. So.
Okay, great. I'm completely happy with that as an answer.
Yeah.
Sorry.
No. Go ahead.
And so, like, the majority of the story that you're telling right now, this is from your paper, Dimers, Networks, and Cluster Integrable Systems, or are there kind of other things?
Yeah, it's mainly from that paper. I mean, most of the things I discussed today were known earlier because they are from Goncharov and Kenyon paper and from this Gekhtman-Shapiro-Tabachnikov-Vainshtein paper. And well, in my paper, I explain how to connect the two together. Yes.
Okay. Great, thanks. That's kind of all the questions I have for me. I'll follow up with the email if I think of anything else.
Okay. Yeah, thanks. Please do.
Okay. Thank you.